If you spin a physical top, it slows down continuously, shedding energy in a smooth, unbroken gradient. Molecules do not. A molecule's energy states are strictly discrete and layered. They do not glide between states, they snap. This infographic compares the three distinct ways a molecule can store energy, establishing a strict stacked hierarchy: rotational, vibrational, and electronic. Look at the first column. Rotational energy requires the least input. The energy gap here is small, placing these transitions within the low-energy microwave and far-infrared regions of the electromagnetic spectrum. The middle tier is vibrational energy. This governs the physical stretching and compression of molecular bonds. The energy gap is wider, requiring infrared radiation to trigger a transition. The highest tier is electronic energy. Moving an electron up into a higher molecular orbital demands a massive energy input, corresponding to the ultraviolet and visible light spectrum. These energy modes do not exist independently. They stack on top of one another structurally. The total energy of any molecule is the sum of its electronic, vibrational, and rotational states. Because a physical molecule cannot isolate these motions in a vacuum, absorbing a single high-energy photon often triggers a simultaneous coupled transition across this entire hierarchy. This slide details the rigid rotor model, which we use to understand the foundational rotational state of simple diatomic molecules like hydrogen chloride or carbon monoxide. Looking at the rotational energy equation, the allowed energy levels depend on the rotational quantum number, J, but the crucial physical variable controlling the energy spacing is the denominator, the moment of inertia. That moment of inertia is dictated entirely by two physical traits: the reduced mass of the specific atoms and the exact bond length between them. This diagram outlines rotational selection rules. The top box shows the primary quantum rule. Molecules cannot spin up or down arbitrarily. They can only absorb or emit radiation by changing their rotational quantum number by exactly 1 unit. But there is a secondary physical requirement for an electromagnetic wave to successfully couple with the molecule: the permanent dipole rule. Compare hydrogen chloride on the left to nitrogen gas on the right. An electric field can only rotate a molecule if it has an asymmetrical charge distribution, a permanent dipole. Because common homonuclear atmospheric gases like nitrogen and oxygen lack this permanent dipole, they are rotationally invisible to microwave radiation. Because the energy spacing relies so heavily on that moment of inertia, reading a molecule's specific microwave spectral lines provides a direct mathematical method to calculate the exact sub-nanometer bond distance between its atoms. Stepping up the energy scale to the infrared region, this slide replaces the rigid bond with the harmonic oscillator model. Atoms in a molecule are not perfectly fixed. Their bonds stretch and compress like springs. The specific vibrational frequency of that spring is determined by the bond's physical stiffness and the reduced mass of the atoms involved. But there is a quantum anomaly. At absolute zero, classical mechanics suggests all motion stops. Quantum mechanics forbids this. Having exactly zero energy violates the Heisenberg uncertainty principle. Even at absolute zero, a molecule retains a baseline zero-point energy. Its bonds are never perfectly still. For a perfect harmonic oscillator, the fundamental vibrational selection rule is rigid. A molecule can only transition up or down by exactly one vibrational quantum number. This flowchart illustrates the rule for infrared activity. A vibration only interacts with infrared light if it temporarily changes the molecular dipole moment. Look at carbon dioxide below. Its asymmetric stretching and bending modes temporarily shift its charge distribution, creating a dynamic dipole. When these dynamic dipoles absorb outgoing infrared radiation, they convert that light into internal vibrational energy. As these excited molecules collide with atmospheric gases, like nitrogen and oxygen, they transfer that energy as heat, the physical mechanism driving the greenhouse effect. In physical reality, molecular vibration and rotation do not happen in isolation. This energy level diagram demonstrates that a single infrared photon packs enough energy to alter both vibrational and rotational states simultaneously. Look at the fundamental transition. The molecule absorbs radiation, moving from the vibrational ground state up to the first excited state. But it must also change rotation. Follow the arrows sloping left. This is the P branch, where the molecule gains vibrational energy but loses 1 unit of rotational momentum. Follow the arrows sloping right for the R branch, gaining both vibrational energy and rotational momentum. Now, direct your attention to the prominent gap in the exact center of the absorption spectrum. For simple diatomic molecules, a purely vibrational transition that does not change the rotational state is strictly forbidden by quantum selection rules. This empty space, the forbidden zero-change transition, is known as the missing Q branch. A single high-resolution infrared spectrum is a composite code. The center frequency reveals the bond strength, while the precise spacing of the P and R peaks mathematically reveals the exact atomic masses and bond length. This grid maps the highest energy tier, electronic transitions. These require massive light inputs to energize electrons into higher molecular orbitals. These jumps dictate the specific wavelengths a molecule absorbs and emits, determining its color, driving photosynthesis, and allowing OLED displays to function. But why are some vibrational transition lines vastly stronger than others during these massive electronic jumps? The intensity of the resulting transition relies entirely on the Frank-Condon factor. This is a measure of how well the vibrational wave functions physically overlap before and after the rapid jump. This potential energy diagram introduces the Frank-Condon principle. The SysX rely on mass disparity. Electrons react instantly, while nuclei are heavy and sluggish. Because nuclear positions cannot adjust during the split-second electron jump, transitions occur vertically on the graph. The bond length is frozen. A molecule strictly prefers to execute electronic transitions where its pre-jump nuclear vibration pattern matches its post-jump pattern. This table shows that even with perfect Frank-Condon overlap, an electronic transition must clear specific quantum symmetry hurdles to be permitted. Look at the top row, defining the spin selection rule. Total spin cannot change in an ordinary electric dipole transition. Shifting from a singlet ground state to a singlet excited state is allowed, but jumping from a singlet to a triplet state is strictly forbidden. The middle row introduces the Laporte-Sillotson rule. For highly symmetric molecules, the overall parity must change during the transition. A shift from symmetric to antisymmetric is allowed, but symmetric to symmetric is not. These forbidden transitions occasionally sneak through via mechanisms like spin-orbit coupling. Engineers exploit these rare, weakly allowed transitions to boost OLED display efficiency. This synthesis diagram brings all 3 tiers together. Unlike a simple atom, a molecule possesses all 3 parameters simultaneously. Notice how the green vibrational structure and red rotational fine structure are nested deep within the larger blue electronic transition. Because a molecule is a physical structure, an electronic jump inevitably alters the bonding environment, instantly triggering a cascade of simultaneous vibrational and rotational shifts. The gray box displays the master formula. The total spectrum equals the electronic transition, plus the vibrational structure, plus the rotational fine structure. Because every energy state is rigorously quantized and governed by strict symmetry rules, every molecule generates a unique, hyperspecific spectral signature. This complex dataset lets us identify the chemical composition and physical conditions of a substance, whether it's in a lab on Earth or drifting through a distant nebula.